Welcome to the sets of the popular TV show Let's Make a Deal. Meet your host for the day, Monty Hall, who stands next to a wall studded with 3 closed doors. Behind one of them hides the car of your dreams, while the other 2 are empty. The rules are simple. Guess the right door and the car is all yours. The show starts off with Monty asking you to pick the winning door. Since no one except him knows where the car is, your choice is as good as random. After you've taken a guess, Monty decides to spice things up a bit. He carefully examines the remaining options and reveals an empty door from one of them. This leaves you with 2 shut doors, and you're still not sure which one holds the car. At this point, he offers you an opportunity to swap doors and pick a new one. Remember, this will be your final choice, and you'll take home whatever comes with it. The question arises, should you accept the deal and switch doors, or stick to your initial choice? Shouldn't the odds of winning the car be equal with both doors? Over the years, the Monty Hall problem has baffled the living daylights out of several statisticians. To solve it, we need to dive deeper into the science of probability. Despite being terrible fortune tellers, humans continue to study and apply probability in various fields where knowing the likelihood of an event's occurrence might be helpful. For instance, insurance companies call upon probability while estimating premium rates for their health policies. This means that their plans for a chain smoker would be significantly costlier than their offerings to a non-smoker. This is because smoking is a statistically proven health hazard that escalates a person's probability of developing serious illnesses. This poses a huge financial risk for the insurance companies that counter it by charging outrageously high premiums. Friends who play rock, paper, scissors to decide who gets to eat the last slice of pizza are using probabilities to break their tie in a fair way. Even genetic traits like gender, eye color, handedness, and dimples are governed purely by probabilities. The earliest traces of probabilities were found in the statistical heritage of ancient civilizations like India and China, where rival kingdoms used it to estimate the size of each other's armies. Despite this, it was only during the medieval era that probability blossomed into a dedicated discipline of mathematics. The onset of this period was marked by the gambling dilemma faced by Frenchman Chevalier de Mere, who was confused about betting on the simultaneous occurrence of 2 sixes while rolling a pair of dice 24 times. In 1694, he decided to seek help from mathematician Blaise Pascal, who in turn discussed the idea with fellow statistician Pierre de Fermat. Together, they went on to lay the foundations of classic probability, which is relevant till date. According to the classical approach, the theoretical probability of an event is defined as a ratio of the number of favorite outcomes and the total number of outcomes. This value lies strictly between 0 and 1. Since the number of outcomes in the favor of an event would always be less than or equal to the total number of outcomes, the maximum probability we can attribute to any event is 1. In case there are no favorable outcomes for an event, its probability equals 0. In other words, it is impossible for that event to occur. Events with extreme probabilities take place all around us. The probability of the sun rising in the west is 0, while the probability of its setting in the west is 1. In the Monty Hall problem, we wish to calculate the probability of winning a car in the event of switching doors when offered a choice. To do this, let's think of a configuration and run through all the possible outcomes. We assume that the jackpot is hidden behind the second door, while doors 1 and 3 are kept empty. If our initial choice was door 1, then Monty would be compelled to open the third door since the second one hides the car. This leaves us with 2 choices, door 1 and door 2. To win the car from here, we'll have to swap doors and ditch our first pick. In case we choose door 2 at the start, Monty would be free to reveal any one of the remaining doors since both of them will be empty. In this situation, we'll lose the car by switching doors. Hence, we must stick to our first guess. Lastly, if we picked door 3 in the beginning, Monty would have to open the first door. Our final choices will now be doors 2 and 3. Once again, we'll win the car by swapping our choice. As can be observed from this table, switching doors when given an opportunity to do so results in winning the jackpot on 2 out of 3 occasions. The same probability drops down to 1 out of 3 cases when we decide to retain our original choice. Therefore, probability suggests that it's best to swap your doors whenever Monty offers you a chance to do so. In the Monty Hall problem, a vast majority of people assume that both doors are equally likely to contain the prize. It's hard for them to believe that swapping doors will get them closer to the jackpot. Truth be told, you're more likely to be attacked by a shark than winning the world's most popular lottery. Even though we can't always predict the future, we can certainly pursue probabilities to get closer to our desired results, and in this chapter, we'll try to do precisely that.